Okay, in this example, we are told that we have a hopper. It's a commonly used device used in the handling and storage of particulate materials, things like grain, such as the grain silos you hear, where you might have some corn or wheat or something stored in these silos. And the hopper design typically consists of a bin section, that's the cylindrical portion, all over a converging section, that's the kind of funnel-shaped part, with a hole at the bottom, that's where the material feeds through. And one interesting or neat thing about hopper flows or flows of particulate material is that the flow rate from the hopper exit is independent of the height of the material sitting above it. So whether if the material was way up here, some tall height above the exit, or if it was down here, actually that's probably not the best place to draw it, but let's say it was here. Either height, the flow rate actually remains the same. It's independent of this height for a sufficiently tall distance above the exit. And the reason for that actually has to do with the fact that with particulate materials, you can get shear stresses against the wall that help support the weight of the material, something that you don't get typically with fluids. Okay, so we know that from experimental measurements that the flow rate from the exit is actually will be a function of the hopper exit diameter, acceleration due to gravity, the angle of the hopper walls, so we'll make that the angle with respect to the vertical here, call it theta. The friction coefficient between the particulate material and the walls, so just what the friction coefficient is as it slides against the walls, and the friction coefficient between the particles themselves, as well as the bulk density of the material at the discharge plane. So what we're going to do is perform a dimensional analysis to determine the dimensionless quantities that govern this flow. And if we use the same hopper and particulate material, how will the mass flow rate from the hopper change if the hopper exit diameter is doubled? So if we double the exit diameter, how does the mass flow rate change? And how does the discharge rate found in part A for this particulate material compare with the mass discharge rate expected for a liquid? All right, so let's do this dimensional analysis. Step 1, we're told that the mass flow rate for this hopper is a function of, we'll just go through the list here. It's all given right here. So we're told that it's a function of the hopper exit diameter. So we'll call that capital D. Let's just call it capital D. The acceleration due to gravity, G. The angle of the hopper walls, theta. The friction coefficient between the particulate material and the walls, let's call that mu W. So that's the friction coefficient with the walls. We're told it also is a function of the particle friction coefficient, so we'll just call that mu P for the friction coefficient between the particles themselves, and then the bulk density of the material at the exit plane, rho B. Bulk density is just, it would be the density of the particles including the void space. So if we have a bunch of particles here, and I just drew a volume around it, it'd be the mass inside that volume divided by the volume. So it's the density of the particles, including the empty space around the particles, divided by the volume. So we have all these variables that we do know are important based on some experimental evidence. So we know the mass flow rate is a function of these things. Now let's go through our dimensional analysis approach where we find out what the basic dimensions are for the variables. So for mass flow rate, that'll be mass per unit time. Diameter, that's a length. Gravity is a length per time squared. Theta, that's an angle, that's dimensionless, so it has no dimensions to it. Same sort of thing with the wall friction coefficient, that's dimensionless. It doesn't have any units with it, so we don't have to include that. Mu P, that's already dimensionless. So these terms right here, the theta, mu W, and mu P, those are all actually pi terms already because they're dimensionless. Theta is dimensionless because if you express it in radians, it has no dimensions associated with it. So anyway, these are all dimensionless quantities or pi terms already. And then we have the bulk density, which will be mass per unit volume. So if we look through this, you'll see for a moment we need a mass for sure, we need a time for sure, and we'll need a length for sure. They're all repeated. The length and time and mass are repeated here. So we need three reference dimensions to describe all these variables. So that's coming up in step 3 here, where we find the number of pi terms using the Buckingham pi theorem. It's the number of variables minus the number of reference dimensions. So the number of variables is 1, 2, 3, 4, 5, 6, 7. Number of reference dimensions is 3. We said it was a mass, length, and a time. So we expect to have 4 pi terms. So now we'll find those using the method of repeating variables. So the first pi term will involve the mass flow. Oh, I guess we need to define our repeating variables before we go any further. Okay, so for repeating variables, we'll need 3 of them because we have 3 reference dimensions, and we want to make sure they have a mass and a length and a time in there. The ones that I'll choose will be the diameter of the bin, so that'll give me a length. Then I'll choose gravity because that'll give me a time, and then I'll also choose the density because that'll give me a mass. So D, G, and rho B will be my repeating variables. Actually, they're the only ones I can really use here. So in this case, everybody should have the same repeating variables. And the reason I say that is because we don't want to choose m dot because it's the dependent variable. It's on the left-hand side of the equation. So we don't want to use that as a repeating variable. If you did use m dot, then it would get buried inside all of the terms on the right-hand side. And you don't want to do that for your dependent variable. It makes the equation very complicated. So we can't use m dot. We can't use theta, mu w, or mu p because they're all dimensionless. They don't have a mass, length, or a time in them at all, so we can't use those. And then you're just left with 3 variables left over, just the d, g, and rho b, so those have to be our repeating variables. So then we'll make our other terms dimensionless using those. So the m dot term will be we're going to make that a pi term, so that'll be m dot times d to the a, g to the b, and rho b to the c. And then we'll go ahead and gather terms, or actually let me write it in terms of the reference dimension. So m to the 0, l to the 0, t to the 0 on the left-hand side because it's dimensionless. And then on the right-hand side we have mass over time for the mass flow rate. We have length raised to the a, length over time squared raised to the b, mass over length cubed raised to the c. Now let's go ahead and gather terms. Like for the mass, we'll have 0 on the left-hand side is equal to 1 plus c on the right-hand side. The length, 0 on the left. On the right-hand side, it'll be a plus b minus 3c. And time, it'll be 0 equals minus 1 minus 2b. So just a reminder of how I get these things. Let me just focus on the length one. So I'm just writing down the exponents. So I have 0 on the left-hand side. And then here I have L to the A, so that gives me the A there. L to the B, that gives me the B there. And then L cubed raised to the C power. So this will be L to the minus 3C. When you take a power and raise it to a power, they just multiply together. So the minus comes from it being in the denominator, and then the 3c's because they multiply. So that's what I've done to get all 3 of these. So if you look at that for a moment, you'll see that c is equal to minus 1. This one tells us that b is equal to a minus 1/2. And then here, this one gets a little more complicated to find a, but we'll have 3 times a minus 1 gives me minus 3, but then we have the negative here that makes it a positive 3. And then positive 3 with a minus 1/2, that'll make it, that'll be, I'm sorry, 5 halves. So a will be equal to the minus 5 halves. So then when we write down our pi term, it'll be m dot times d to the minus 5 halves, g to the minus 1/2, rho b to the minus 1. Or, just written a little more cleanly, m dot all over rho b times the square root of g times d to the 5 halves. So that's our first pi term. Now the other non-repeating variables are just the theta, mu w, and mu p. They're already dimensionless. So they're already their own pi terms. So pi 2 would just be theta, pi 3 is mu w, pi 4 will be mu p. And we should have 4 pi terms, right? So from the Buckingham pi theorem, we have 4 pi terms. So here are all 4. So let's go ahead and write out our, well, first of all, we should double check that everything is dimensionless. So we know that pi 2, pi 3, and pi 4 are already dimensionless, so they're okay. Pi 1, we'll just plug in mass over time times length cubed over mass times t over length to the 1/2 times 1 over length to the 5 halves. So the masses cancel out, times cancel out. The denominator here will have L to the 1/2 times L to the 5 halves. That's L to the 6 halves, which is just 3, so the L's will cancel out. So everything's okay here. Don't forget to do this check where you just verify that each of these terms are dimensionless. It can be pretty useful to catch little mistakes. So then our final expression in dimensionless form looks like this. So our mass flow rate is a function of the wall angle, the wall friction coefficient, the particle friction coefficient, and it's made dimensionless like this. You'll see there is no height of material in here because that wasn't part of our original list of variables, because we know it's not dependent on height. Just from our, we said in the problem statement that that was the case. All right, so that's our expression for the discharge rate from the bin. So let's go back to our set of questions here. So we did part A. So if the same, let's do part B. If the same hopper and particulate material are used, so that means that the theta, the mu w, and the mu p all remain the same. How will the mass discharge rate from the hopper change if the hopper exit diameter is doubled? So the right-hand side remains the same because it's the same hopper. The question is, how does the mass discharge rate change? So we'll have, let's write it down like this. In the first case, we'll have rho b 1 g1 d1 to the 5th. So first case, we just have that, our measured mass flow rate, our bulk density, gravity, diameter of the exit. And then in the second case, what we're going to do is we're going to double the diameter, right? So we're asked to figure out what happens if we double the diameter. So what we want to know is what happens if we just double the diameter. So just keep in mind that the theta, the mu w, and the mu p are exactly the same, right? We said we're using the same hopper and the same material, so those will be the same. And actually, the rho b will be the same too. So let me just write this out, and then we'll make use of that information. So since this quantity, the variables on the right-hand side are the same, we'll have the same value for the function on the right-hand side, so that these will be the same, whether I use, for the first case or the second case. The bulk densities will be the same because, again, it's the same material. Gravity, of course, is the same. So then m dot 2 will equal m dot 1 times the square root of d2, or yeah. Let me rewrite that. Instead of square root, it'll be d2 over d1 to the 5 halves. But we're told that the diameter doubles, so d2 is 2 times d1. So m dot 2 will be m dot 1 times 2 raised to the 5 halves, which comes out to be something like about, let me put this on the next line. If you just plug that into a calculator, that comes out to be about 5.66 approximately. So if we double the diameter of the exit, we'll get a mass flow rate that's just over 5.5 times faster. It's kind of an unusual number, but it's because we're raising this value of 2 to the 5 halves. So that's how we can predict what the mass flow rate will be for a different sized hopper exit. All right, the very last part of this problem, let's go back up to the problem statement, is compare the discharge rate found in part A with the mass discharge rate expected for a liquid. So for a liquid, we know the height does make a difference. Let me draw this picture. For a liquid, the height makes a difference. Here's the diameter of the exit. To find the mass flow rate for the liquid, let's call it m dot L, that's just going to be the velocity at the exit, V, times the area of the exit, which will be, and then there's going to be a density in there as well, sorry. Density of the liquid times the velocity at the exit times the area of the exit, which will be pi d squared over 4. That's just the mass flow rate at the exit. To find the velocity of the exit, we can apply Bernoulli's equation from this point at the free surface down to the exit. So let's call that point 1, call that point 2. So we can write out Bernoulli's equation. The z here is, I'll just measure from the base pointing upward. Remember, gravity is pointing downward. So from Bernoulli's equation, the pressure at 1 is equal to the pressure at 2. They're both just atmospheric pressure, because at 2 it's just discharging into the atmosphere, so that's a free jet. Velocity at 1 is about equal to 0. We're assuming that it's a large diameter here, so that this top moves down slowly, so the kinetic energy is negligible. V2 is what we're trying to find, and Z1 minus Z2 will be equal to the h, here the height. So we can plug these in to our Bernoulli's equation and simplify it, and you'll get that V comes out to be the square root of 2gh when you plug that in, and then we can plug that back in up here. So the mass flow rate for the liquid will be the density of the liquid times the square root of 2gh times pi d squared over 4. So that's the mass flow rate for liquid. And up here, we have the mass flow rate for a granular or particulate material. So they're quite different behaviors, right? So we said already that if you doubled the diameter of the exit for a particulate material, the mass flow rate will go up by a factor of 5.66. If you double the diameter for a liquid, the mass flow rate will go up by a factor of 4. So doubling the diameter gives you quite different behavior here. You also see that for liquid, the mass flow rate is dependent on the height. Of course, here we said that it didn't depend on the height. Both are dependent on the density and the square root of gravity. You see that showing up in both of those. And then, of course, a liquid doesn't have any dependence on the angle or friction coefficients. That doesn't show up for the liquid. So some pretty significant differences whether you're dealing with a particulate material like sand flowing through an hourglass or liquid in this kind of geometry. So very different behavior. All right, we'll go ahead and end the example there.